Last time we saw the relevant group of transformations that preserve the wave front, the light wave front. If we call lambda, is the one that preserves this metric tensor, the Minkowski metric, right? Now, today I want to introduce the four vectors. Why? Because like in ordinary space-only physics, we write all our equations in terms of vectors, right? Like Maxwell equations that we wrote the first day. And the reason there is that if you write your equations by using three-dimensional space vectors, they are automatically invariant under rotations, right? That's the reason why we write using vectors. Even though at the end of the day, when we do computations, then we have to work with components. So the idea here is that instead of writing vector-like equations by looking at objects like three-dimensional vectors that are invariant under rotation, we look to objects that are invariant under this particular form of rotation that are the rotation and Lorentz boost in space-time, so four-dimensional space-time. So we want something like an arbitrary vector. So now I don't know because this is for the three-dimensional. So let's call it like this. So this is an object that has components, right? But it has four components instead of three. So it has so A naught is the component along the time-like direction. So if you write, and then the three-dimensional part. So you have the x, right? So this is the thing that. Unfortunately, well, so think this is the three-dimensional space of which I draw only, say, two components, and then you have the time-like component like this. So this is a vector, but it's a vector in a four-dimensional space, okay? So you must be, by now you should feel comfortable thinking of vectors in n-dimensional spaces, right? I mean, it doesn't matter. So this is a particular case. It's a vector in four dimensions. And the only part, I mean, something that, so this, you can write it, write the usual, by using the components. And it goes from, say, 0 to 3, right? Whereas 0, we look at the, or sometimes you see it like this, A0 and then the vector part, right? So that you remember the space, three-dimensional space component. That's the old vectors that we already knew, and then it has a component in the time-like direction. In this language, the generic boost that we study, the Lorentz boost that we study last lectures, is going to be, so it's a transformation, right, that mixes the time component with the spatial one. So you have a boost in a certain direction, so you get to transform the zero component with this gamma. Remember, gamma is 1 over the square root of 1 minus beta square, A0 minus B. Okay? So this is and this is 1 over the square root of 1 minus beta square. So if this is the direction of the boost, right? So then the component in that direction, so you have to introduce some, so let's call the component parallel to the direction of the boost, get boosted up. And the one that are transverse to the direction, there are two more, right? Those are left unchanged. So this is the generic boost, generic Lorentz boost. Is this clear? I mean, So you see they are more symmetrical in this notation because you remember, if you want to go back to the one with t and x, right, you have to remember that this is like a ct, right? This is ct, so you get an extra c down here. You get the results that I wrote the other time. But in this form, as component, so this can be, for instance, the coordinates, but they can be any vector, okay, any vector. And we are going to write like velocity, acceleration. Those are 4 vectors as well. And this is true for any vectors that can be written in this form. So from now on, we stick to this notation. And as we have the scalar product, we have the scalar product of 2 vectors, right? That is an invariant. Similarly, here we have the scalar product of two 4 vectors. Right, so it's something like this, and clearly this is a convenient way to write this. I can write it with this notation, so I have E, the basis vector, so alpha dot the beta, right, and then here you have the corresponding component of these 4 vectors. This object here, that is the scalar product of the unit vectors in the is what I call G, but maybe it's better to call it eta alpha beta. That is the metric tensor. You see, it tells you how you do this scalar product. And if you remember, this eta alpha beta is not just the Kronecker symbol, because it has this -1 here, right? So this is the metric tensor for this space. So for 3-dimensional vectors, you could have done the same, but in that case, this eta would have been this part here, so it would have been just the identity, right, that you write as a Kronecker. But because of the Minkowski property of the space, this is not the identity, it has a -1 there. And in fact, in general, you can write the measure, a distance in this space, right? Like that is not like eta alpha beta dx alpha dx beta, right? This is the generalization of the usual distance, in which you just have here the identity matrix. Then here you have dx squared plus dy squared, right? But here is not, because it's like minus c squared dt squared plus dx squared plus d. What? These square. I think there's something stuck. Okay. Or in general, say it's minus. You see a. Well, it's like here, so I can write minus a b naught plus a, where this is the usual scalar product of 2 3-dimensional vectors. Okay. So this space, that is our extension of the 3-dimensional space, is called the Minkowski, the 4-dimensional Minkowski space. So I don't know, Minkowski 4. And is the space where we actually live. And it becomes relevant, as we already discussed, when the velocities that we are studying in our system become close to the speed of light. Because otherwise the fact that we are in a 4-dimensional space is not so evident. Okay. And what is important about this quantity? Well, it's the same as in 3 dimension, right? The scalar product was important because it's an invariant under rotation, and here's the same. It's invariant under this Lorentz transformations on top of the usual rotation. So these are invariant quantities, are the same for all systems connected by Lorentz transformations. So if you did you know about these 4 vectors before? Have you? Or is the first time you you heard? 4 vectors. Is that? Yeah. Well, I don't know. I'm asking. Okay, if you're comfortable with this, then we can start writing some. We want to study some dynamics in this space, in particular, then for electromagnetic fields and charged particles. So we need the extension of familiar ideas, like what is the velocity? So the 4 velocity. So the extension of the ordinary velocity. So this is usually called u. So let's take 2 components. So it's a 4 vector, and you want to define this. You see, now the difficulty is that the velocity is the space is the time derivatives of space, right? But now it's a bit tricky because you see, the usual velocity is a vector because it's the derivative of a vector, right? Because t is the scalar, so you take the derivative, x is a vector, so this is a vector. But now this is not longer true because t itself is just a component of a 4 vector, the coordinates. So if you take this, it's not going to give you a vector. So what you have to introduce is the derivative of the coordinate, right? But with respect to an invariant that is called the proper time. So the proper time is essentially the time marked by a clock that moves with the observer, okay? And that is, it has to do, so this is called the proper time. And you see that now these are the coordinates that we already decided there are 4 vector because they transform in the way I wrote under Lorentz transformation, and therefore the 4 velocity is a vector as well. What is the relation between this proper time and what we call time? Well, you see, the proper time is defined to be, usually in this form here, is essentially, so you take an interval, this you know that is an invariant square, right? The interval in 4 dimensions, and you divide it by c because that gives you in units of time, right? So this is the definition of this proper time. So essentially it's the distance in units of c. But then you see that you can write this, so it's the square, so I have to take the square root. So ds square is what I wrote there before, right? So let me write it here. It's minus 1 over c square, right? That multiply what? Minus c square dt square plus the vector-like part, right? So you see that I can take the square of that, right? And I have the c, 1 over c, right? C square dt square minus dx square. And if you pull out now the dt, if you pull out the dt and you pull back the c, you see this gives you the relation between this proper time and the t as 4th component of the coordinate for momentum. And this is, of course, is this 1 over gamma. So this is like dt over gamma. And this is the usual beta factor of the Lorentz transformation. So if you wish, this is this retardation effect that you have in going from the proper time to the t time as measured from the other observer, right? So this is the connection between the two. But really what you need is the proper time in this context. That is the local time of the observer. So if this is the 4 velocity, then what are so then we can, just to understand a little better, let's look at the individual components one by one. So the time component, the u naught, right, is the dx naught divided by d tau. But we have seen that the dx naught, right, the dx naught is what? The x naught is defined to be t times c. So it's c dt divided by d tau. And d tau is this thing here, so it's 1 minus v squared divided by c squared. So that's the time component, and the other components, so the u vectors, the other three components, these are the dx vector, the proper time. Okay, so I can write this in the usual dt, dx dt, that's what I call v, the velocity, and then I have the derivative of dt with respect to tau. So you see that again, dt over d tau is just this factor. So here I have the usual v divided by this factor 1 minus v squared. So if you want, this is this contraction, or with respect to time, this retardation effect due to the Lorentz metric. So the space-like components of the four velocity are essentially the usual velocity. In fact, I can always go to the limits in which v over c is much smaller than 1, and this goes exactly in what we call the velocity up to today. And the same here, this goes simply to the speed of light. So the time-like component is just the speed of light in this. In fact, in general, I can write the u alpha or u bar, right? You see, it's like there is this factor gamma that you can pull out 1 over, so it's gamma c v. This is the four velocity if you want to split the time-like component from the space, three-dimensional space component. And then you already know how they transform, like velocity, because they transform as the component of a four vector, so exactly like the coordinates, so it's the one I wrote there. So you don't have to redo all this stuff, the sum over the velocities, you know, how do they, everything is encoded here. You don't have to worry about all these strange rules that you derive for relativity. It just comes from writing everything in this four vector notations. Okay, so questions? You think, is it useful, or do you like these four vectors or not? I think they are kind of neat. And what we are going to, I mean, this is the language in which from now on you should write all your equations. This is my point, because I mean, unless you work in solid state physics, I mean, so if you are working in high energy physics, everything is very close to the speed of light, so it's relevant to write it in the correct language. So as before, you were very careful to write all your equations with vectors, so that you were guaranteed that by rotating nothing would have happened. Now you have to do the same with the same care and writing everything with these four vectors. And we are going to write in a second, or maybe in a few minutes, Maxwell equations and Lorentz force in this language. But before, I have to give you some exercises for Monday, that I guess is the last, your last chance to do some homework. So the first, maybe I should mention that in some, so I wrote the Minkowski metric in this form, right? Of course, this is not completely unique. In some books, you will find this other metric. Okay, so I guess I don't know what somebody. It depends which one you study first. And then it's very hard to switch. I suggest you stick to this, but this one has the, you see, it has the wrong sign on the time and the right sign here. So in a way, I think it's more, it reminds you that the odd guy is the time. No? The other one would be just the opposite. You have this positive and that minus. So, but I don't know. I mean, I think most of the recent books use this metric. Some of the older, they use the other one. But okay, everything is exactly the same, but it's like the units. It's like you know, as everything is the same as long as you are consistent. I mean, you have to use the same method. I'm saying this because so first write what is the scalar product of so verify that the scalar product of the square of the four velocity is equal to minus c squared with this metric, of course. Otherwise, it flips. Okay, that's kind of trivial, essentially. Then, so 1, 2. By using this, maybe maybe I should add a footnote here. Clearly, now that you have the velocity, it's easy to introduce the momentum, right? So you can have the four momentum that is going to be just what? If you multiply by the mass, this quantity, right? Is going to be your four momentum. So you see what are the now that's kind of interesting in the sense that now if you look at the component of this object, you see that the zero component, so the p naught is just m. That thing there, right? Is m. So if you use this, is mc divided by 1 minus v squared c squared. Actually, mc, yeah, MC. And p, well, then p is just mv. And so this again in the non-relativistic limit, this goes in the usual momentum, and this goes into this essential the mass time the speed of light. Now, if you, I mean, this quantity here in really old books is called the mass, and then this is called the rest mass. Meaning the mass measured by the observer. So if I measure my mass, that's my rest mass. Then if I start moving and somebody is measuring that mass, that is this mass here. This is a completely useless concept. I think let's call m is the rest mass, and that's the only mass that is sensible to measure. Then this is just the boost factor due to the fact that you are moving with a certain speed, if you agree. Otherwise, just call this the rest mass. Then, you know, you have all these discussions about, you see, as this goes close to the speed of light, then this mass diverges, and then that's the reason why you cannot go faster than light. But I could never really understand this. I think it's just that there is no boost to the speed. I mean, that it requires an infinite boost to go at the speed of light. So, I mean, there is only one mass. That's the rest mass. I don't know. But then, okay, you see, so if you draw, here you have time, right? And here you have space. And you have your trajectory, per se, in space and time. Then it's kind of neat, you see, because this is like energy in a way. So the component in this direction gives you the energy, and the component in this direction gives you the momentum. So the components, they may change, and that's already suggesting how you see, you get a lot of concepts that were separated in the ordinary language of Cartesian coordinates, three-dimensional space. They get unified in this language because you see, for instance, energy and momentum were separated, right? It was P and E, but now you see essentially the energy is a component of the same object, that is the force momentum. So if that was the force velocity, this is the force momentum. That already is telling you that energy and momentum, they are not they are not separate concepts. And in fact, after having told you this, you can try the second exercise. That is to show that the rest mass of a particle is linked to its energy and momentum by the very famous E equal, well, I guess I want to write it like this: E square is equal to m square c square plus p square. I have a c square here. Well, I guess. Okay, well. No, I think it's like this, right? Because p square. Because this is a p square, right? This is the units I'm thinking. So these are the same units. This is an energy, but okay, check the correct one. So I think the one you are thinking is the one with the fourth here, right? Okay, whatever. I'm just used to take c equal to 1, so I'm always... No, well, you have to use this to rederive this. This, of course, is the very famous E. If you go to a frame in which this is not there, this is equal to mc square. Right, that you read on a T-shirt. But the correct one is this one, right? This is a special case if you are in a frame at rest with respect to the energy you are measuring. And third, you can take the limit of V, the non-relativistic limit of this, and study what is the energy in this limit. Okay, that's very quick. And of course, I guess what is new here is that you have this relation between the mass, the rest mass, and the energy, right? That means that, again, before we thought of the energy and just the kinetic energy, right? And now you see that even for a particle at rest, you have a lot of energy in the mass. Because from here you see that the mass is part of the, you see, this component, the mc square component of the, is just a component of a 4 vector, so they can be reshuffled around, okay? So, but I mean, that's not, were you about to?
I don't know. In this case, this mass is the mass of photon or...
No, I mean, the photon has 0 rest mass. This is a particle, a massive particle. So a massive particle is a particle that has a mass, a finite mass in the rest frame of the particle. The photon, well, you are not even supposed to know about the photons, but no, I mean, the photon is exactly massless. It's very important. No, it's very important because otherwise there would not be, you remember all those radiation fields that those they go down 1 over r, but if you have a mass, they go down much faster. I mean, if you give a mass, even a tiny mass to the photon, then the radiation field goes down much faster than 1 over r. So we know for sure that the photon has a mass. I mean, if it has a mass, it's really, no, it's really tiny.
Yeah. So this mass is relativist or...
No, that's what I said. I don't understand this distinction.
It's relativist.
But what is a relativistic mass?
So M, you can write them by this relation.
This is, for me, when I write M, is the rest mass. Because it's the only one that you can measure. I mean, the rest is some. Any other questions?
Do this mass change with...
No, the rest mass does not change. It's an invariant. It's a scalar.
But when we pass from a referential frame to another...
Well, what you see is this sort of... but that's not the mass. It's just the fact that is the Lorentz boost on the time component of the momentum that you are seeing. Then if you want to call this the mass and this is the rest mass, you are welcome, but at the end you confuse yourself. I assure you. Because then start thinking, you see all these things in the books that they are kind of, I mean, it's simple like this. What is the mass is what you measure to be the mass. To measure that, you have to be in the same frame of this object. So it's the rest mass. Then there is no other objects. Then you have 4 vectors, 4 momenta, and then components of this. Stick to this, you never embarrass yourself. Yes.
I want to know how, because when p equals 0, there is not a motion. So where from this energy?
Where does it come from?
Where does it come from?
Why you have this? Well,
P equals 0, okay.
I mean, because the energy is not a scalar any longer. Is a component of. You see, the energy is a component of a 4 vector, essentially. And this component has parts that come from the momentum, right? Depending on the frame of reference. So the momentum carries energy, and all these things get mixed up. So the fact that a lot of energy is frozen into the mass is just a question of who's observing these things.
So, if there is not another kind of mass, I think the second Newton law should fall.
Well, we are going to write, the second is F equals ma, right? Yeah, we are going to write that because all you need is to write an acceleration. I wrote the vector and the momentum, so I'm going to write an acceleration, and then you have Newton's law. You see, I mean,
We are going to assume the mass like inertial
it's going to be, the inertial mass is the rest mass. But I don't understand what is worrying you.
Before you said there isn't just one mass.
Well, I mean, yeah, this.
Yes, okay. If there isn't just one mass, I think the second law, the second Newton's law, will fall because
No.
how can we?
It's going to be modified. We have to write the Newton's law in this 4-vector language. So we'll have a 4 force that will be equal to the rest mass times a 4 acceleration. Then when you insist, you see, your problem comes only when you insist in splitting this. Then you sort of call this part, the old velocity, but I think I'm going to do that. But before, I want to give you a few more so actually this 4 vectors notation is useful to solve a large number of exercises in which you have particles. So we are back to this sort of point particles, but they just sort of so take point particles like electrons, and let's take also the photon and assume that is a particle as well. But of course, it's a special particle because it has 0 mass, right? So by using this, we can do many exercises that reproduce important results. For instance, you see that the conservation laws is just that the sum of the momenta before and after some collisions must be the same. And this is the full conservation. You see, in one equation, you have the energy conservation and the momentum conservation. So in particular, for instance, you can show that a well-known result, that a free electron, okay, cannot emit or absorb a photon. Did you know that? If you have a free electron, so a little guy here going around, it cannot emit or absorb a photon. So if you hit it with a photon, so how do you convince yourself that this is the case? It has to do with the conservation. So this is the exercise, though. So call P gamma the momentum of this photon, and PE the 4 momentum of the electron, right? And then it's going to be a 4 momentum of the electron after let's assume that is absorbed. So at the beginning you have 2 momenta, then at the end you have the final momentum of this electron. It's just an exercise in kinematics. So by using prove that it's not possible. Or, in other words, it's only possible if the energy of the photon is 0. But if the energy of the photon is 0, that means that you don't have the photon, because the photon has no mass. So the only thing that can have is energy. If you take even the energy away from the photon is gone. Right? Prove that it's not possible to... So in other words, you write the conservation law, that is this, right? You have the sum of the 4 momenta. So I drop these things from now on because we only have 4 vectors. So if I write something like this, this is the 4 vector. So this is the conservation. So take the square, do something, massage this thing until you get something that is impossible, unless the energy of the photon is there. And then you have proved that. So you see, okay. You need a bound electron in order to have emission, or you need the field to conserve the energy in order to have that. So all these atomic spectra are only possible. So you don't have atomic spectra for a free electron because of this. Yes?
I saw on some papers that they push a limit for photon mass,
Yeah.
even if it is small.
Right.
So
Yeah, because that's the experimental physics, right? You never believe what the theorists tell them. But it's correct. You measure. In fact, I think the first chapter of Jackson's is about the measure of the mass of the photon, and you see the bound is I don't know, 10 to the minus.
Very, very small.
It's very tiny. Of course, we have a stronger argument because you see, the fact that the photon is massless has to do with the gauge invariance that we discussed of the Maxwell equations. And if you believe that the equations describing the electromagnetic fields are gauge invariance, then it follows that the mass is zero. I'll show you this the last minute of my last class, if we have time. But in your mind, you must think, okay, from the theorist point of view, the photon is massless because Maxwell equations are gauge invariant. So, in other words, a mass term for the photon would break gauge invariance explicitly. Since we believe that gauge invariance is a fundamental symmetry, or better, a fundamental invariance of nature, we are pretty sure that they will never find a mass for the photon. For the same reason, we are pretty sure that you'll never find a neutrino moving faster than light, because we believe in Lorentz invariance. Okay. Anything else?
For massless particles, what we talk is about their helicity, right?
That has to do with the spin of these particles, or the polarization, yes.
Yes. So is this thing always true? I mean,
This is always true.
okay.
No, but this is not, it has not to do with the helicity, it's just the conservation of four momenta. Therefore, conservation of energy and the momentum. Do you know about Compton scattering? Have you studied this? Okay, so the last, so another homework. Well, try to do as many, you have to do just this twin stuff, right? No other exercise so you have time to. You remember this Compton scattering is a different problem, right? Is that you have a photon and an electron, and then an electron and a photon. So it's a different process. You have also a p gamma prime. Okay, so that is allowed. So by using the same arguments, you should be able to derive the famous Compton formula that the wavelengths of the wavelengths of the photon of light coming off after the scattering is related to the original one by this h and e 1 minus cosine of theta, where theta is the angle, the scattering angle, okay? So I guess to do that, you only need to know that the p gamma of a photon is can be written like this. Well, this tells you the direction, I don't know. This is the direction of this momentum, right, in space. So what I'm saying, because you see, this is the energy, so this will be the frequency, right? And you know that there is this, I don't know, it's called the Planck, no? I think this is really the frequency. The nu lambda is equal to h, right? Or omega is h. Nu lambda. No, you're right. I mean, what? Help me. A? No, what is that? P, yes, P. Ah, yes, okay. And then, okay, then that's right, yeah. So it's like this. Okay, sorry. I'm a little. A. So it's like this, right? So this is the electron. This is called a Feynman diagram. Well, there are many exercises that you can try and solve. I don't know if you have time. Whatever. About this E equal mc square, you can you can measure, for instance, this. So this is about E equal mc square, right? Just to get a feeling of the enormous amount of energy that is stored in the mass. If you So you can do these computations. If you go to a gym and you know they have this sort of standing bicycle, and if you go really fast, essentially you produce a power of half horsepower, roughly, on a bicycle. So 1/2 horsepower. That's roughly is 74. Well, actually, is exactly 746 watts. Now, if you have let's assume, so people go to do that because they want to slim down, right? They want to lose weight. So assume that the efficiency of this process is, I don't know, 25%, because clearly it's not completely, so only one fourth. So compute by using this relation how long do you have to go to the gym to lose, say, 1 kilogram. We are talking years here, I mean, just to get you an idea. Huh? Well, do the computation, you'll be surprised. So you need to compute, you know, well, it's clear. No, you only need this. This is horsepower. Just this is the power that you use this 746 watts, because this is in CGS. So then you multiply by the seconds in 1 year to get how much energy you are consuming. Then you convert into a mass to get 1 kilo. And of course, since you have this huge factor, you are going to psych for a long time. So I want to know how long is that time? How many years? Then you may wonder why people go to the gym. But of course, you lose weight. You're not losing this weight. You understand, right? You're losing fat. So this is a chemical process that you burn fat, and this is a completely different things. So indeed, if you go to the gym, you lose weight. But of course, the best way to lose weight is not to eat, as you know, because our body is extremely efficient. So say you run, and you know, I mean, you run for I don't know, half an hour, you lose I don't know, 200 kilocalories. How much food is 200 kilocalories? Do you have an idea? You know, one of those snacks that you have, you eat that's 200 kilocalories. So, I mean, we were designed to survive with very little energy. So, I mean, the only way to lose weight is not to eat, I think. To go to the gym is good for other reasons. I mean, okay, so that's Those are your last exercises. I think, or maybe I have some more. So as I said, I'm running a little. So first I want, so before we hit the Lorentz force and all this stuff, it's useful to, so what is the equivalent, the most basic exercise, if you want, with Newtonian mechanics is the uniformly accelerated motion, right? If I drop this chalk here, it's a uniformly accelerated motion because gravity is pulling with a constant acceleration on the body, right? And we know the solution is 1/2 gt squared, right? Clearly, this cannot be the result in general in special relativity because something cannot be indefinitely accelerated, right? Because otherwise you will move faster than light. So something must take place here, and so this is the problem. Okay, so let me now take to avoid further embarrassment with these C factors. Let me take C equal to 1 now. I guess, well, no. So I have just to make the problem a little more interesting. So you have a rocket that accelerates with a constant acceleration g, let's say 9.8 meters second square, and you launch these things. So how is the trajectory in space-time according to this what we learned? Okay, so that's the basic problem in dynamics. And so I have the rocket. I want to be on board of this rocket. I want to have a gravity like on the Earth, so that I can I don't float around. So the best way is to have the rocket accelerate as g. Then you are like in an elevator, and so inside. In fact, this is Einstein elevator in a way, because if you are inside and you don't have windows, there is no way that you can tell whether you are on a rocket moving with constant acceleration g, or you are in a gravitational field, right? That was Einstein's observation and the starting point of general relativity. Okay, that's another class. But so how I want to solve this problem, and it's a bit. So let me try to solve it. First, I write the velocity. So I know that the for velocity of this rocket, what is this? This was exercise number 1. So it's c squared. So now in this nice units, it's just -1, right? Then I have the acceleration. Now, an important property of the four acceleration is that it's always orthogonal to the 4 velocity. So you define your acceleration. You do that, and you discover that is always orthogonal. Maybe this should be an exercise. So this is just du d tau, right? Because I define the velocity to be dx d tau. So this, if you know, if you see, but this follows from this, right? So okay, convince yourself that this is true, that a dot u is equal to 0. But it's already in here. You see, this is a strange, this is a vector that has constant size, right? Because you see that the square of the vector by itself is constant. So if you take the time derivative respect to the proper time of this quantity, you get something that will necessarily have this property. So, but please do it and convince yourself. So you see, it's strange. The this is not true in the ordinary space, right? Three-dimensional space where the acceleration certainly is not. I mean, it can happen that is like in circular uniform motion where the acceleration is in fact orthogonal, but in general it's not true. But this is always true that in four-dimensional space the full acceleration is always orthogonal to the. And what is the square of the acceleration? Well, this depends on the problem, but in this case we have decided that the acceleration is constant and has a value g. So these are the conditions that define my problem. So if I solve those, I should get the solution. In fact, I will get Newton's law for this, how I will apply to. So you see, so let me write this. So this is minus u0 or ut, whatever your pref, ux square, right? And this is minus at, the time component or zero component, ut plus ax ux. And this, of course, is a t square plus a x square. So I'm assuming this is the direction x, so everything, whatever happened in the y-z direction, I don't care because I'm moving in a fixed direction that I decided to call x. So the other components I can neglect completely. So from this one, okay, let's write it this way. You see that I can write at, the time component of my acceleration, okay, is equal to ax, I take it on the other side, that is 0, times the ratio of the two components of the velocity. On the other hand, from this one, you see that you see this is proportional to ax by this factor. So this I can write it simply as ax square 1 minus ux ut square, and this must be equal to g square. So from this second equation by using the one I just derived. On the other hand, from here I see that take this, divide both sides by ut square, then you get that 1 over ut square is equal minus 1 plus the ratio of ux square over ut square, right? But you see this is
minus 1 over ut square.
1, yeah. Thank you. So now I can take this and replace it there, right? So that in fact I get just 1 over ax squared divided by ut squared. Or, in other words, from the last one, I get that the x component of my acceleration, the x component of my acceleration is the t component of the velocity times g, right? And the t component of my acceleration, is the x component times g. Okay, so I've reduced the problem. I found the component of my acceleration in terms of the components of my velocity. Therefore, now if you see this thing here is the acceleration. So let's take the derivative of this so that I can replace. Take the time derivative, the proper time derivative of this. So this was already the proper time derivative of the ux. So now is the second time derivative of the x component of the velocity with respect to the proper time, right? I'm taking proper derivative here and here. So, yeah. Where? This? No, it's 1 minus, because you see, it's minus, minus. So I take this on the other side. No, but it goes on the other.
Yeah, if you got it the other side, it becomes plus. Nothing like that. Should tell them.
I mean, change, right? So you say it's plus. So if you take so then on this side, g is a constant, so this is just g d u t d proper time, right? But this is the acceleration, right, by definition. So this is g a t, so it's g squared u x, yes.
Why you change there?
Why?
Yeah. It's just minus 1 square. Minus 1.
Where?
It was correct, I mean.
Yeah, this. I think it's correct. Let's.
It's fine. Negative, you choose
Yes.
negative, negative.
That one will be positive. This is 1, then it's positive.
Positive divided by minus. Positive divided by minus.
What? Huh?
They are confused because of this equality sign, I think.
Yeah, it's okay. It's okay.
Can I?
Sir, why we choose the plus 1? X squared is u plus square, g squared, right?
No, I don't. I just. Why to choose?
Ax squared is ut squared times g squared, right?
You mean I took the square root?
Yeah.
Because they you want them to be positive, so I mean you have the choice, but no. Let's take I mean, strictly speaking, you have a plus and minus, but let's take the positive. So now I have an equation that I know. So now I want to find the velocity, right? And you see now I have an equation that I know how to solve, because the second derivative of this minus g squared, the function, equal to 0. So that is not, I mean, it's not a trigonometric, it's again this sinh hyperbolic cosine. So the solution of this differential equation must be a combination of, say, a sinh of g tau plus another constant that depends on the boundary condition, the hyperbolic. In fact, I can fix these boundary conditions by let's assume that at beginning you start from rest, at rest, so you have a 0 component, and you see that by definition then there you start with say at the initial proper time with this constant acceleration, right? Now these conditions, you see, you want at the time tau equal to 0 then therefore this must be equal to 0. And also because you want that to be exactly equal to g, this is equal to 1. So that's your solution. The solution of this motion is the space-like component of your for velocity, that is the derivative of the position with respect to the proper time, is the sinh, right? And the t component, the other component, you see, is just the is dt d tau, so it's the hyperbolic cosine. Do you see that? Because of this, right? If this is the hyperbolic sine, you see that the hyperbolic sine minus the hyperbolic cosine is equal. So from there you get the other. And now you can integrate this because you have the velocity. So if you just take the integral with respect to the proper time, it's going to give you the trajectory, because I get x as a function of the proper time, not the time, is the integral of this. So it's 1 over g, the hyperbolic sine of g tau minus 1, right? That is the integral of this. And t of tau is just the one that satisfies these boundary conditions. So you see, in this language, the trajectory of your particles, you write it x and t as a function of the proper time. So it's very different. Before we were writing, for us, the trajectory in Newtonian physics was the x as a function of t, little t. Now t is just another component of the vectors of your position in space-time, and they are both parameterized not by t, that is a component, but by the proper time, that is the clock that is running with you. So remember, now the position of an object is a vector in space-time. So it has 4 components. In this case, just 2 components, because we collapsed the 3-dimensional space along just one direction. And to describe the motion, you have to tell me the position and the time as a function of the proper time. So that's the solution of the problem. In fact, here you have now, if you use this solution, for instance, let's t is the time of somebody who stay behind, right, on the Earth. Here is t. Tau is the proper time on the ship. So if you wait 40 years, so you stay back on the Earth, you go to the gym because you want to lose that famous kilos, and you wait. So you go on for 40 years. You'll see it's not enough to lose that kilo, but still you keep on going, and then you ask what is the proper time after 40 years on the Earth on the ship, right? Well, to get that, you just need to invert. You see, this is your trajectory, so you need to take g on the other side, then take the inverse function of the hyperbolic sine. So I guess tau is is roughly 1 over g, the inverse function of 40, because it's t, times g. There is this is equal, and then now g, if you take c equal to 1, is roughly, if c equals 1, g is like 1 over time. It's about 1 year. So you can essentially put 1 here in these units. And therefore here it's of 40 that I check is roughly 4.4 years. if you take the inverse hyperbolic function of 40, you get 4.5. So you see, the proper time on the spaceship is just just 4 years and a half, and so that's the usual things that brings back to the twins. That the guy who's moving very fast because he's accelerating, so very fast is moving very close to the speed of light. Time is much slower than for the guy who's left behind. As measured by the guy here. Because remember, the paradox comes from the fact that it is completely symmetric for the guy on the other one. And yeah.
What is your explanation about this time which goes like a sine
That's your. This is a coordinate. It has this shape. So the trajectory. Let me draw the trajectory. I can draw this. So if this is x and this is t, right? Now your trajectory is this curve. So it's something like this. I mean, c is equal to 1. So the speed of light is. And so you start somewhere here. So this is before you start, and then you move like this. This is your trajectory. Because you see, x plus 1 over g square minus t square is equal 1 over g square, right, from this equation. So you can draw this curve, and it's this curve here. So you start at t equal to 0, you start from some point that you, and then you move in this form, and you see you never reach the speed of light, right? Light is like a horizon. You never penetrate beyond, and that's the way it is. I mean, you shouldn't think of time as time. Time is just a coordinate in this xt plane. And you are following the motion with the... So what you call time is really the proper time. That is the ticking of this clock on board of the ship. So that's really the proper time, what we think of time. But time as a coordinate of space-time is a very different thing, and in this case it has this shape. You see, so this is the solution of the uniformly accelerated motion. Of course, at the very beginning, right? Okay, well. Okay. So that was a basic exercise in relativistic dynamics, but now we really don't, I mean, this is only accessory to our study of the electromagnetic field. So let's move on to the next step. So I wrote the velocity, accelerations, and all this stuff in this language. So how about the Lorentz force? Lorentz force, that's where we started. And back we are, right? So so this we wrote it in three-dimensional space as the ma, the change in momentum for a particle with charge q is E, the electric field, V over C cross B. Now I'm in CGS or this Gauss unit, I guess. So I want to write it now. I hope we agree now that this is not the best way to write this equation, because we want to write it in this space-time invariant form or covariant form. So I want to use a manifestly covariant form. So I have to rewrite that in terms of this object that I introduced, that is the 4 momentum. So let's put it here, the 4 momentum. So this is the 4 momentum, and I also hope that I convince you that t is not a good parameter in this problem. I should use the proper time. Okay, t is not a good parameter because it's a coordinate. Okay. And this I like to write it in a form that is a little bit. So let's write it like this: QC. Then here I have. You see, I'm trying to write this as a product of something. So here I have some 0 component of some velocity plus the space component times v. Okay. So these things here should be a 4 vector, right? Because this is a 4 vector. So let me put it. It's a 4 vector. And then, therefore, this combination, I pull out the C so that I have common V and vectors here. So this object should be a 4 vector, okay? And I assume, because I had the velocity here, I'm guessing, but I put the velocity also here, although the time component of this velocity. So how do you get, you see, you want to get the vector by multiplying something by a vector, right? So it's a QC, this is a scalar. And then the only way, so you see, if you put, so let me put it like this. dp alpha d tau, this is a QC, then this is proportional to a velocity that I promote to be a 4 velocity, but then to go from a 4 velocity back to a velocity by multiplying something, you need a tensor here. Right? There is no other way. Otherwise, it's only proportional. But you don't want this to be proportional because you know that the force is not proportional to the velocity because it gets twisted by the electromagnetic field. So that means that this is the generalization in 4 dimensions of the Lorentz force. But unfortunately, you have to bring in what is a 4 tensor. If this was a 4 vector, this is a 4 tensor, meaning a tensor, 2 indices, but these indices run from 0 to 3, right? While all the other tensors, they were running only over 3 components, okay? And what are the components of these tensors? Well, you can read them off from this because you want to get this back, right? And if you do that, maybe this is an exercise or just, you see that it's a tensor that has these components. So on this, the time, time, well, first of all, is anti-symmetric. So it has zeros along the diagonal. Then the mixed component time, space are given by the electric field, while the space components are components of the B field. And because it's anti-symmetric, you know that this must be these others. So you see how beautiful it is. In this language, you don't have the electric and the magnetic field. You have a unique object that is the electromagnetic 4 tensors, usually indicated as F alpha beta, the component of which are the component of the electric and the magnetic vector fields, arranged in that way. In fact, you can check that when you project this down, so let's check what we get now. If you take the component alpha equal 1, 2, 3, that is the space component, you get exactly Lorentz force. You can check, in fact check. I mean, it takes a second. Check it. How about so this is actually a good generalization because it goes back to what we had if we stick to the space part. How about the time part? So the time part is P0 d tau. Then I have to pick so this is now is fixed to 0. So I'm reading these components here. And you see that you get the charge QC, then you see this is just the scalar product. You see, you fix this to 0, so you are reading these directions. So is the scalar product of E times V. And you see this is CDT, so if you you get rid of this, and P0 is the energy, right? So you see that's correct because this is the energy in the process. Actually, it's the power, right? Because the energy is E times E times the velocity gives you the change in energy.
So
Yes.
here the four-vector tensor is traceless, right?
Traceless, because it's anti-symmetric.
Okay, what does this imply? I mean, does it have any physical meaning?
Well, because you see, it has only, you see, 1, 2, 3, 4, 5, 6. You want this to have 6 independent components because you start out with 3 plus 3 independent components. So a 4 by 4 arbitrary tensor has many more. It has 16 independent components. But if it is antisymmetric, you understand that it has only 1, 2, 3, 4, 5, 6, because the others are. I mean, it must be 0 component here on the diagonal, and the others are simply the same change by sign. So the requirement that you only have 6 independent components, this must be antisymmetric. I mean, it's not a physical requirement; it's a requirement of the number of independent components in this equation. So now. Then I stop. We have, so this tensor is what replaces our E and B field strengths, and therefore I must be able to write the Maxwell equations in this language. And to do that, I have to introduce 2 things. First, I introduce, you see, in the Maxwell equation, I have the charge density and the current densities. So wouldn't that be beautiful to have these 2 to be components of the 4 vectors? And indeed, they are. Is a 4 vectors C times rho J. And the other thing you need to know is that, again, you can pull together in a 4 vector the gradient and the time derivative. Therefore, you can introduce the alpha to be defined as this, and you understand this is minus the x0 plus, and the gradient as a space component. You see how everything. Therefore, for instance, the conservation law is very simple, right? Because d alpha g alpha equal to 0. And if you take d alpha f alpha beta, so you take the 4 derivative, so this is the 4 derivative, this is the 4 current, if you take the full derivative of this electromagnetic tensor, this is equal, now I'm using Gauss unit, because these notes are in Gauss units. This is 4 pi c g alpha. And you can check, so this is check it too, write the components, and you will see that this equation gives you back the two Maxwell equations that are those with the charges and currents densities, that is Gauss and Ampere, right? And how about the others? You see, the other two are the one without the charge density and the current density, are sort of a constraint on the structure, right? It's the one that tells you that the divergence of B is equal 0, that essentially is, say, it doesn't tell you what B is, but it tells you that B must be divergenceless. And similarly, the other one is with the curl of E and the time derivative of B. But you see, in this language, time derivative and curl, they come together. And they come together, and so you have this equation here. So again, try to write back the components E and B here. Right here, this is a derivative. And you will see that this equation gives back the two other Maxwell equations, the one without charge and current density. So that's good. That's what I wanted to rederive. So now we are back to our first lectures. We are back to Maxwell equations, but now we rewrote them in this more efficient formalism that relies on 4 vectors and 4 tensors, that is, objects that live naturally in 4 dimensions. And you see that it's much more compact. And so now we will study these equations directly and rederive some of the results. That's what is left. In particular, for instance, in this language, it's trivial to derive the linear vector potentials, right? Because, of course, also the potentials, right? You understand, maybe with the C, the scalar potential. I mean, you have a C, but let's stick with C equal to 1. So also the scalar potential and the vector potential, obviously, they fall into a 4 vector. And therefore, you see that the questions to compute the potential for instance, a charge moving with constant speed that we sort of spent last time trying to derive, then it becomes just a matter of Lorentz transformation of a Coulomb potential to a frame that is moving with constant speed, right? So if you apply Lorentz transformations to this component, when you take this equal to 0 and this equal to a Coulomb potential, then you boost it to a frame that is moving with velocity v. That's exactly a charge moving with velocity v, and you derive the potential in just a single line. This is the power of the language, right? And so we will do that, and then yeah, I'm running out of time, and then I want to write the Lagrangian, because at the end of the day I promised that we will write. So I want to write the Lagrangian from which it's possible to derive these equations and this, and then we are essentially done. So if we have time, we will also rederive the radiation field, that, as you will see, is much simpler in this language, because you simply do the Fourier transform in 4 dimensions, and then everything becomes much simpler. than what we did before in 3 dimensions. Okay?